I'm staying in Cambridge right now.
Okay, good. Yeah. Usually people will be slightly late, so let's wait until probably 5 past. Is okay?
Okay, yeah, sounds good.
Yep. Also, by the way, 2 days ago, I met Tailin Wu in person.
Oh, cool.
Yeah, he was sharing with me the work with you on compositional energy-based generation.
Oh, yeah, yes, yeah.
Yeah, yeah, and I mean, it's very interesting.
Cool, yeah. Uh, yeah. What is your experience at NUS? Oh, by the way, no one can everyone hear us or uh
Um, can anyone hear us? You can type. Okay. No, if no one reply, I can um
oh,
I can ask my I think some people in my team are here. I can ask them as well. And um I think Chen is here. Chen, if you can hear us, can you Slack me or type in the chat? Yes. Okay. Good. Okay, and the Q&A also works. Okay. Good. Yeah,
oh, it works. Okay, I see.
it works. They can hear us. And
Okay.
the Q&A function also works.
Oh,
So later
awesome. Okay.
during the talk, we can use the Q&A to for people to ask questions or something.
Okay, sounds good. Sounds good.
Great. Yeah. So what is your future research focus after you become independent?
I think still roughly, I've been working a lot on compositional generative modeling, so I'm pretty interested in extending that a bit. I think a lot of my research has been towards constructing intelligent embodied robots. So that's another part I want to keep on doing. So I think roughly using this idea of compositionality and generative modeling to try to construct more in general purpose robots is
So are you going to use only the simulator, or are you going to buy real robots and run your algorithm on them?
I also have real robots.
Okay. Okay, that's
Yeah.
good. That's good. Yeah.
Yeah. And then I think also, so the institute I'm in has a lot of neuroscience folks. So I'm kind of interested in trying to take some inspirations from neuroscience to get better robots.
Okay,
Uh,
that's very good. I mean, that's what I'm interested in as well. I'm a large portion of my research focus on cognitive science inspired machine learning, and so that overlap with the neuroscience people and the cognition people.
yeah, makes sense, makes sense. Yeah.
Yeah,
Yeah, and I guess also because I feel like that Harvard has very strong science department, so I might do a bit of AI for science also, just since
yeah.
there are so many people who are in the
Yeah,
same
they are
area.
very good in scientific research. I mean, nature science. So that's I mean, I think that's one of the biggest advantage of Harvard over another school focusing on computer science.
Yeah, I think so. So yeah, in general, I want to be a bit more disciplinary. So it'd be good to like be able to work with people from lots of areas.
Yeah, you will find there are some advantages of doing that, or also some disadvantages. I have been doing this for like the past 7 years, and so people talk in different languages in different departments. Yeah,
Oh, I see. So it can be hard.
yeah. I'm
Makes
curious
sense.
about one thing. If you are using real robot to do those learning or training, they cannot accelerate, right? So it's physical world. And is
Yeah.
that very slow and very expensive to run them?
It's pretty slow. Yeah. So the experiments is very slow to run. Uh, yeah, it's also kind of expensive. Yeah, because each of the robots are around $100,000 or
Yeah.
a couple $100,000. So it's both yeah, it's both a bit slower and a bit more expensive, but much faster than biology and much cheaper than biological experiments.
Oh, I see. Yeah, if I end up doing more like reinforcement learning or word modeling, I probably will try to buy some robot. I mean, 100K is still considered cheaper end for compare with biological experiments.
Yeah, it's much cheaper compared to biological experiments.
Yeah, well, that's a good idea. Yeah.
How do you like Singapore so far?
Also, actually, I lived in Singapore for 3 years. So before I started my undergrad, so I like it a lot. It's a very, how to say, it's a very well organized society, and it's extremely safe and extremely efficient if you do routine stuff, right? But
Makes sense.
however, compared to US, like Boston or California, the energy and diversity of creating new things, of course, is not there compared. It's not the same level compared to Boston and California, and also
Makes
the dynamics between communication between different fields, such as startup doing robots or people doing machine learning research or doing biology. This is not as good as North America. Yeah, so that's the situation. But this is becoming better. It's getting better.
Makes sense. Makes sense.
Yeah. Are you going to ICML, by the way?
Yes, I'll be at ISML.
Okay, I will be there. I will see you there. See you in Vienna.
Okay, yeah, we can do that.
Yeah, then I will spend a few days in ICML, and then I'm heading to Italy to meeting one of my collaborators there, and yeah, so it's good. It's good to see you.
Oh, fun, fun, fun.
Yeah, good. Let's wait for 2 more minutes,
Yeah, sounds good.
and we can get started later.
Mhm.
Oh. So for everyone on this call, if you have any question, there's if you're unfamiliar with Zoom, on the lower right corner, there is a Q&A button. If you click on that, you can post questions, and it's either Yilun will see them and answer the question, or if necessary, I can open your mic, allow you to speak as directly. Depends on the complexity of the question. So feel free to use the Q&A function of the Zoom for question for question and interaction. And I think that's pretty much it. I think we can get started.
Oh, okay, sounds good. I can just start presenting.
Oh yeah, I think I can give you a short introduction. So hi everyone.
Okay, yeah, sure.
Yeah, good. So for people who don't know Yilun is currently a PhD student, going to graduate very soon from MIT. And let me open up your bio. He is supported by the National Science Foundation Graduate Research Fellow, and he was a research fellow at OpenAI, the company doing ChatGPT, and he was a visiting scholar at Facebook AI Research. Well, he was a student researcher at Google DeepMind. His work has recently received best papers at the iClear, which is one of the 3 top machine conference, and at NeurIPS, another conference, and the ICRI workshop. He will soon join Harvard University as an assistant professor. Yeah, thank you so much. So I will pass the time to Yilun.
Okay, great. Thanks so much for the introduction. And today I'll talk a bit about this idea of compositional generative modeling. And feel free to ask any questions during the talk. So overall, the idea I will talk about is towards this general goal of trying to get intelligent general purpose AI agents in the physical world. So if we look at current robotic systems, the things we can do in the physical world are very simple. So we can put a single mug on top of a rack, or do a simple task where we place a cup on the floor and we put a bowl on top of the cup. What we really want to do is we really want to get these intelligent physical systems that can operate autonomously over the period of many months and years, and solve a variety of tasks that we've never seen before. So we really want to get intelligent physical robots in the world. And I think the systems to get to a place where we can actually get these intelligent robots is a question of generalization. How can we get systems that can really robustly generalize to unseen tasks, environments, and other agents? So overall, in this talk, I'll talk about a general approach towards solving this task, and then I'll talk about a couple key components and results. So the overall general approach I'll talk about is this idea that if we can learn probabilistic generative models or world models of the world, then we can really use this as a useful tool for generalizing. And I'll talk about 2 ways in which these generative models allow us to generalize. The first idea is this idea that generative models really allow you to flexibly predict and actually plan that test time through search. So let's look at the task of climbing up stairs. So if we train a neural network to do this task, typically this neural network takes this input image, as well as the task climb up the stairs, and it outputs a single action trajectory. And this is really good when the training and test distributions match. So if we train this robot in this house, and then at test time, we give it a similar house, this works. But one issue with training neural networks to predict actions in this way is that if the environment changes, let's say there's suddenly an obstacle in front of the robot, now we don't know what to do because this output action trajectory is no longer valid. And basically, one thing we can do to really help us solve this issue is this idea that we can really encode preferences over actions. And this is exactly the idea of learning a generative model, or in this case, I'll talk about energy-based model over your actions. So in this setting, now we learn a model that takes as an input an input image, as well as a trajectory of actions. And this network predicts a single scalar energy, which corresponds to an energy landscape across all the actions the agent could take. So once we have this neural network, where if it's a probabilistic generative model, this energy is simply the likelihood. Then we can essentially use this energy to represent the negative utility of an action, so that if an action is good, the utility is low, or the utility is high, and otherwise the utility is low. And now, if we formulate a generative model using this energy perspective, the benefit is that now we can use search to infer the right action. So once we have this energy landscape and this input observation, I can now search for the action trajectory that minimizes my final energy. This allows us to really generalize at test time because it allows us to really add new test time constraints to the robot. So now we can take our energy function, which is this top pathway here, and we can simply define a new energy function for costs over actions. For example, we want to make sure that a robot is safe, that it preserves battery life, or like it avoids a barrier. And we can really encode these new test time constraints as new energy functions. And since everything is represented as an energy function, now I can take the energy function for climbing upstairs, and I can add the energy function for each of these constraints to get this new energy landscape. Now I can use search or optimization over this energy landscape to find actions that satisfy both the original task we trained it on, as well as these new constraints, and get a valid action. So essentially, by predicting actions, by modeling energy landscapes, instead of just explicitly predicting a final action, we can now use search to generalize to new settings. We can use search to find an action that satisfies new constraints. So that's the first idea of how really world models can allow us to generalize. The other idea is how we can really construct generative models compositionally, so that we can even construct generative models where we don't have any training data at all. So we've all seen that that in the past couple years, language models have been able to do really fascinating things. So if you ask a language model how to construct AI, it can give you these very precise step-by-step instructions. At the same time, if we add multiple modalities into language models, so if we consider a multimodal language model, and even if we give it a very simple task in the physical world, such as this image, and we ask it the question, is the blue cup below the red bowl? It will answer nonsensibly and give incorrect answers. So while generative AI has started to work pretty well in natural language, it is still very poor in many embodied tasks. And I think this has to do a lot with the distribution of data we see. So in natural language, the training distribution is roughly similar to the real-world distribution, because natural language is constructed by people and is very information-rich and relatively homogeneous. In contrast, if we consider the distribution of images and text, or the data an embodied agent will encounter, this is a much more heterogeneous and diverse mixture of data. So here, the data might consist of combinations of images, of actions, of objects, of language. So the space of possible inputs is much, much larger. And the available data we have to train our models is a very narrow slice of the entire real-world distribution we would want our system to operate over. So this is why when we consider embodied data or many real-world distributions, it is difficult to just construct a single generative model that can work well for all the situations we want the model to operate over. So in this talk, I'll also talk about how this idea of energy-based models provides us with a way to really take this narrow slice of data we have and really have it be able to generalize across this whole area of the real-world distribution. And the key idea is this idea of compositionality or factorization. Instead of representing our distribution P of X as a single monolithic generative model, now we learn a set of generative models that capture separate independent factors of the data. So we learn a generative model over one axis, and then we learn a separate generative model over a second axis. And now, when we take the product of these factors, we can now have a generative model that is able to capture the entire area of data, even though we only have a small amount of data in this diagonal slice. And in general, now these factors are also much simpler to learn because instead of having to capture all the variations of language and actions, now we can learn a single model for language, another model for actions. But this comes with this caveat that your data might not actually have this factorized structure. So this can be a biased estimate of the joint distribution. But I'll illustrate that this still provides us a powerful tool to enable generalization. Another side point to note is that, or actually a question, is that over the last several years, we've seen how generative models have gotten astonishingly better as we've increased the size of the models. So if we look at generative models in 2015, compared to 2018 to 2022, the generative models have gotten significantly better. So a question is, should we just gather as much data as possible and just throw it in one single generative model? Well, if we actually look a bit closer at what has changed in generative models over the years, we'll see that not only has the scale of the generative model increased, but so has a lot of different engineering tricks to make the generative models work better. One really major change is this idea that instead of having a generative model distribution P of X over all possible images, we now learn class condition generative models or text condition generative models. So the uncertainty in the distribution we model has become much simpler. At the same time, we've also stopped generating samples from the distribution we've learned. So in 2018, we started generating these low temperature samples. And in 2022, we started drawing samples from this classifier-free guidance distribution. That's not the original base distribution we've learned. So if we take all the skill we've used to train these giant generative models in 2022, and now we start removing these things, we see that the samples actually are still very poor. So if we simply sample from the conditional distribution learned by the original generative model, given the prompt an astronaut riding the horse, we can see that it's much, much worse than images we normally see from this model. And at the same time, if we draw samples from the unconditional image distribution from the original distribution trained by the models, the samples look even worse. So overall, I think these results point to this idea that generative models haven't just been able to fit arbitrarily high dimensional distributions as we increase their size, but rather ones that are relatively simple. And there are a variety of ways that people have used to make the distribution simple by simply considering either low intrinsic dimensionality of data, such as natural language, or by really richly conditioning on past contexts, such as text prompts. And if we take this view of generative models and their limitations, then we can view compositional generative distributions, which is really crucial for effective text-to-image synthesis through classifier-free guidance. Okay, so that was just a brief overview of generative models, how they can enable you to adapt to new constraints, and how you can really build generative models through compositionality. So now I'll talk a bit more about the details of this. So first, I'll talk a bit about the idea of energy-based models. Then I'll talk about the idea of compositionality. And then I'll talk about how this compositionality enables us to plan. And then finally, I'll talk about how this compositionality enables us to combine multimodal models for heterogeneous decision-making. So first, let me provide a bit more of an introduction on energy-based models and how they enable us to compose. So energy-based model is defined using an energy function. So that if we have an energy-based model for red trucks, then this energy function will take in the image of a green truck and assign it as scalar energy that is high. In contrast, when we have an image of a red truck, it will predict the scalar energy that is low. And essentially, this energy function will parameterize this landscape of or this energy landscape across the space of images, so that all images that are red trucks have low energy, and all other images have high energy. And once you have this energy function can really implicitly encode a variety of different things. So on one hand, this energy function can encode something like utility, which is similar to the example I showed at the beginning of the talk. It can also encode whether you're inside a set or not. And finally, more generally, it can encode any probability distribution you want through the Boltzmann distribution. So in general, an energy-based model can represent any generative model you want. And you can interpret any generative model as an energy function. Once you have this energy function, then now the question is, how do I really sample from the probability distribution defined by this energy function? So what this means is we want to find a data point that has low energy. And this is more complex than it may sound, because the data space is really high dimensional. So it could take a very long time for you to find a low energy data point. So one way you can really help find one way that you can use a neural network to help you find these low energy data points is to use a neural network to help guide your sampling. So the simplest method is to simply take your previous initialize a sample from a random noise, and then use the gradient of the energy function to help you find a low energy data point. In 2019, we proposed, but the issue with the previous approach is it only finds a single energy minima, as opposed to the entire distribution over the energy function you want to capture. So in 2019, we proposed to use Langevin dynamics as an approach to really draw samples for the energy landscape over high dimensional spaces. So here's an illustration in 2D. So in this sampling procedure, now we use the gradient of the energy function to help us find one energy minima. But the added Gaussian noise helps perturb us from the energy minima and allow us to sample to another energy minima. So the combination of both the added noise and the gradient now allows you to sample from the energy distribution. And then if you look at images, it ends up looking very, very similar to the diffusion process. And I'll talk a bit more about these connections soon. But in general, one way to think about this generation procedure under this energy interpretation compared to most other generative models is that it really is much slower than other models because now you have to run all these steps of optimization to get a sample. But it allows you to generalize and to new energy landscapes. So this sampling procedure is agnostic to the energy function you've learned. So you can combine multiple different energy functions or combine energy functions with constraints. And now you can use this procedure to sample from those new distributions. So this is a flexible way to allow you to sample from new distributions at the expense of speed. So now let me just delve a bit more into details. So let's say we have a distribution P of X, and we now want to learn an energy function that so that the learned distribution, e to the negative energy of X, matches the original distribution of samples we got. So you can actually do this for maximum likelihood estimation. And if you take the gradient of the log likelihood, it corresponds to decreasing the energy of real data while decreasing the size of the partition function, or the energy assigned to all other points. And when you expand this expression a couple of times, it becomes this contrastive objective, where on one hand, you draw samples from the data distribution and decrease the energy of those samples, while on the other hand, you draw samples from the model distribution and you increase the energy of those samples. So energy-based models have been a classic class of generative models for several decades. In 2019, we illustrated a scalable method to really train these energy-based models over high-resolution image data sets by using a combination of the Langevin sampling procedure I talked about earlier, in combination with a replay buffer to allow you to more effectively draw samples from this learned distribution. So let me show a visual illustration of this training procedure. At the very beginning, your energy landscape is flat. So both images of red trucks as well as Gaussian noise gets assigned the same energy. And under this new energy landscape, you draw a sample from the distribution, which corresponds to this red dot. And now you contrastively decrease the energy of the red trucks while increasing the energy of the sample data point. And now you have this new landscape that is better shaped towards your real data. And you repeat the procedure. So under this under this better shaped energy landscape, you again draw a new data sample, which is now this noisy truck, which now looks like a noisy red truck. And now you repeat this procedure where you decrease the energy of red trucks while increasing the energy of this noisy truck. And you can imagine that after repeating this procedure for a very, very long time period, now you have a distribution where all red trucks have low energy and all other data points have high energy. And at this point, when you increase the energy of red trucks, when you decrease the energy of red trucks, the samples you draw from your energy function are also images of red trucks. So you both increase the energy of red trucks while also decreasing the energy of red trucks. So training cancels out, and now you have an energy function that correctly models the distribution you care about. And yeah, and actually, as a historical caveat, this training procedure actually was one of the inspirations for GANs. So because this training procedure has been around for many decades. And actually, it turns out that you can also interpret diffusion models as energy-based models. So this was a sampling procedure we proposed in early 2019. So you can see that essentially there's this Langevin sampling procedure. You start from Gaussian noise, and then eventually images emerge from the sampling procedure. So based off our work, there was subsequent work on score-based models, which adopted this Langevin sampling procedure to sample from high-dimensional images. But now, instead of explicitly learning this energy function, they proposed to learn this denoising function using denoising score matching, which was another classical objective for training energy-based models. And then you can view diffusion models as a type of score-based model where the inputs are contracted over sampling. So if you look at the actual sampling procedure, it ends up looking very, very similar to the sampling procedure that we did with energy-based models. So overall, it turns out that you can just interpret diffusion models as energy-based models. So you just interpret this denoising function as a gradient of an energy function. So this allows you to, so whenever I talk about composing energy functions together, you can simply just compose diffusion models together by adding these gradient predictions. And there are a couple forms of composition that I'll talk about later, which require not only this gradient of the energy function, but also the actual magnitude of the energy function. So it turns out that you can actually parameterize diffusion models with energy functions as opposed to score functions also. So this means that essentially you can treat diffusion models as a type of EBM and as a way to implement many of the compositions I'll talk about later in this talk. So in my work, I've illustrated how these energy-based models can be used across a wide variety of domains, such as images, robot plans, natural language, proteins, videos, and 3D shapes. So I will focus primarily on the embodied setting, but a lot of these techniques can be applied across many other settings also. Okay, great. So I gave a very brief introduction into energy-based models. Now let me talk a bit more about compositionality. So let's first define what we mean by compositionality, or like what we want in terms of compositionality. So normally when we think about compositionality, we think about trying to get a neural network that can generate things that satisfy a set of constraints. So maybe we want a neural network that can generate trajectories that reach a particular goal, where the trajectories have a particular gait, and so that the trajectories avoid obstacles. And one easy way to get neural networks to predict outputs that satisfy all three of these constraints is simply by adding loss functions together. So I can just define loss functions for every single constraint I want, and then I can just add those loss functions together and train my neural network to get a predictor with all these properties. So this is a really composable way to train networks with arbitrary sets of properties. But the main issue is, let's say at prediction time, I have three separate networks. I have one neural network that generates trajectories that reach a goal, a separate neural network that generates trajectories with a particular gait, and a third neural network that generates trajectories that avoids obstacles. It turns out that at test time, I can't really combine these neural networks together. I can't take the predictions from the first neural network and add it with the predictions of the second network and the third network. So these neural networks, so if at training time, I know the exact set of things I want my neural network, or functions I want my neural network to predict, then I can just define the loss functions. At test time, I can't construct a neural network that satisfies all these specifications. So it turns out that you can view energy-based models as an intermediate abstraction for prediction, which allows you to compose things together. And the overall idea is now instead of training a neural network that simply predicts predictions that have trajectories that reach a goal, now we learn this energy landscape over all possible trajectories that reach a goal. And similarly, we learn the energy landscape over all possible trajectories that have a particular gate. So by learning this more complex loss compilation, so instead of learning the final answer, now we have this effectively a learned loss function over all predictions. We can now combine these loss functions or energy landscapes together. So we can form a composite energy landscape from the goal loss function, gate loss function, and obstacle loss function. So then this allows us to take the composition of these energy landscapes and then use the Langevin sampling procedure I talked about earlier to construct predictions that satisfy multiple sets of constraints, even if the neural networks themselves are trained on only single combinations. So you can view the energy-based models as a compilation that enables composition through addition at prediction time, at the expense of additional running time. So now let's look a bit more at this composition operation in the space of images. So again, if we have a red truck energy function and we run this Langevin sampling procedure, we get an image of a red truck. But the main power of this approach is now we can take a red truck energy function, which is trained in one way. We can take a separate energy function for desert energy function that's trained a separate way. And now at test time, I can simply compose these two energy functions together. And now I can generate an image of a red truck in a desert. So this is so like the previous example, this shows that you can really flexibly combine networks at test time. And in general, when we talk about these energy functions, there's a magnitude in which each energy function is defined. So you can control the influence that you want to put on each of these energy functions by scaling the magnitude of the energy function. So by default, we use a magnitude of 1 on each energy function. So in general, depending on what the energy function represents, there's a different algebra in which you can combine energy functions together. So if an energy function represents utility, then adding the two energy functions together corresponds to utility addition. In contrast, if an energy function represents sets, then adding the energy functions actually corresponds to set intersection. And if an energy function represents a probability distribution, then adding the two energy functions corresponds to the product of the two probability distributions. So there's a lot of different interpretations and ways to combine energy functions that I'll now go to next. So first, let me talk a bit about set membership functions. So let's say I have an energy function for the blue set. So all points in the blue set have low energy, and all other points have high energy. And let's say I have a separate second energy function where all points in the orange set have high energy, and all other points have low energy. All points in the orange set have low energy, and all other points have high energy. So once we have these two energy functions together, if I add the two energy functions together, I now get a new energy function that exactly has low energy in points that are in both set 1 and set 2. So by simply adding two energy functions together, I can construct a set or an energy function for the set intersection. In contrast, if I take the first energy function and the second energy function, and I take the softman of the two energy functions, I get a new energy function that has low energy at all points in either the first set or the second set. And finally, at prediction time, if I take one energy function and subtract the second energy function, now I have a new energy function that has low energy at all points in one set that are not in the other set. So just by composing these energy functions in these different ways, I can now implement the set operations of intersection, union, and difference. And it turns out that with suitable thresholding, you can also nest these set operations with respect to each other. So let me show an example of the flexibility of this approach. So we've trained one energy function to generate images of a green cylinder behind a yellow cube. And we've trained a separate energy function to generate images of a gray cylinder below a brown cube. So we can use these set intersection operations to now generate an image of a gray cylinder behind a yellow cube and not a gray cylinder below a brown cube. But that's not so interesting. What we can actually do is we can further nest these. So now we can generate a scene at test time of a gray cylinder behind a yellow cube and a gray cylinder below a brown cube, which are these two images. Or we can generate an image of a gray cube behind a brown cube and a gray cube right of a blue sphere, which are these two images. So this really allows us at test time to generate samples from all types of sets. But actually, even more general than sets, this procedure also allows us to generate samples for all types of probability distributions. So we can learn one energy-based model for the distribution P1 of X. We can learn a separate energy-based model for a distribution P2 of X. And now we can use this. We can use the sum of the energies to actually draw samples from the product distribution P1 of X times P2 of X. We can also have an energy function for P1 of X and P2 of X. And we can use a separate operation to actually draw samples from the mixture of the two distributions, P1 of X plus P2 of X. And finally, we can learn one energy function for P1 of X, and we can learn a separate energy function from P2 of X. And we can use the difference of the two energy functions to actually draw samples from P1 of X divided by P2 of X to the alpha. So this form of composing different probability distributions has a wide variety of different applications. On one hand, you can use this for a compositional scene synthesis. So if you have a simple text-to-image model that can generate images given a single sentence description, such as a couch right next to the windows, by composing multiple models together, you can construct much more complex scenes, such as a couch right next to the windows, a table in front of the couch, and a vase of flowers on top of the table. And you can see that this image is much more complex than what the base text-to-image model was trained on. So you get a much simpler image from the base model. You can also use this compositionality to adapt the style of video generation. So you can train a video model that generates videos in a particular style, and then you can use composition to generate videos in digital art, in outdoor videos, or using storybook illustrations. You can also compose these distributions across different spatial regions of an image. So this allows you to specify that I want a portion of Mars here, that I want a giant mecha robot here, that I want the Starship Enterprise here. So it really allows us to controllably generate an image layout from a single text-to-image model. And finally, it allows us to compose different constraints together. So we can use this compositionality to do constraint solving. So we can have one energy function define that we want an object inside a box. We can have a separate energy function define that I want to make sure an object is close to another object, that I want to make sure that the configuration of object is collision-free. And by composing all these constraints together, now we can, by sampling from this product distribution, which we can implement using addition of the energy functions, we can now solve this constraint satisfaction problem. So overall, there are lots of applications. But one additional thing you can do, or actually, before I go there, there are a lot of applications, but one complication is that it turns out as you compose more and more of these energy functions together, the optimization landscape you want to minimize for it gets increasingly more and more complicated. And it turns out that you can help use diffusion models as a way to help alleviate this. So instead of optimizing one single complex energy landscape, now we can learn a sequence of energy landscapes through the denoising, through the diffusion objective, where the diffusion model learns a sequence of T energy landscapes, where the first energy landscape is the original data distribution, and the last one is a normal distribution. And then where each energy landscape is parameterized by the score function. And now, again, the sampling is just simply a contracted Langevin sampling procedure. But the benefit is now you have a sequence of energy landscapes. So you first optimize a very coarse one that's easy to optimize, and then you sequentially optimize for more and more complex landscapes. So this allows you to sample from a distribution P1 of X times P2 of X by simply adding the two denoising functions together. It turns out that there's a bit of complication. So you actually cannot directly just add the score functions together, because the score function for the product of the two distributions isn't exactly the addition of each individual score function, although it's a close approximation. So you can actually formally also sample from this composition and denoising functions from diffusion models, and treating them as a total of T separate energy landscapes. And then you can essentially use annealed importance sampling to draw samples from these T landscapes. So you initialize the sample from Gaussian noise, and then you transition, then you run multiple steps of Langevin dynamics at a particular noise level in the diffusion process. And then you use that sample to then transition to the next energy landscape. And in practice, essentially, it's the same as normal diffusion sampling with these combined score functions. but now you need to run multiple reverse sampling steps at a particular noise level. So instead of just simply running one reverse sampling step at one noise level and then transitioning to the next noise level, now you have to run multiple denoising steps at a particular noise level. And that corresponds to a type of Langevin sampling. So that was a lot of complication. Visually, it's pretty simple. Essentially, to compose distributions together, you simply learn you now learn a sequence of energy landscapes, where the first energy landscape is really smooth and easy to optimize. Intermediate one is slightly harder to optimize, and then the final energy landscape is much harder to optimize. So you just optimize this one, use this initialization to help you optimize this distribution, and use that to help you optimize for this new distribution. And then the question is, so I've talked a lot about how we can compose distributions together, but then one question is, how do we actually discover these components? So let's say I have a training distribution, which is this narrow diagonal slice here. How do I actually discover the independent components that are composed together to form this training distribution? And it turns out that there's also an easy way to really discover these components. And that rough idea is now we represent our distribution P of X is simply the product of independent components. So we just write our generative model as a product of multiple energy functions. So here's an example of this. Let's say I want to reconstruct an image. So I take an input image and I encode it into a set of latents so that I can reconstruct this original, so that I want to learn a density over the reconstructions of this image. It turns out you can just simply represent this density as the product of and the separate densities, where each density is represented by an energy function. So now you take your input image, you infer latent one, simply just add these energy functions together. And now to learn this reconstruction density, you simply just say, I want to learn a set of energy functions so that when I take the latent encoding from each energy function and I add up all these energy functions together, when I optimize this energy function, I get my original image reconstruction. So we simply just change our energy function to be and make it represented by multiple energy functions. And then you can encourage independence across these energy functions through information bottleneck. So if you restrict the size of this latent, the most effective way to encode these images is to make them orthogonal. Cool. So let me show a couple examples of what happens when you infer these energy functions. So on the top here, we have an image consisting of 4 objects. And then each of these energy functions actually corresponds to individual objects in the scene. And at the bottom, we have an image of a face. And now each of the energy functions we infer correspond to different attributes of the face. So we have attributes of people, the background, the skin color, the background, and then the hairstyle. And by taking the composition of these energy functions, now we get original reconstruction of the image. But the main benefit of being able to infer these independent components, which in this case can represent different objects in the scene, is that now we can recombine them in new ways. So we can train one instance of this model on dataset 1, consisting of spheres and cubes. And this model will now infer components that correspond to a sphere and a cube. So these are 2 separate components. The other 2 components would be these 2 spheres. And then we have a separate instance of model that's trained over boots and trucks. And now 2 components would be 2 boots. And so we can take some of the components we inferred from one model, and we can take some other components inferred by a second model. And by taking the composition of these 2 models, now we can, which is a product here, now we can generate these hybrid scenes that have both cubes and spheres, as well as boots and trucks, even though there is no data with all of these combinations. Okay, great. So I briefly talked a bit about energy-based models and how they can compose. So now I'll talk a bit more about how you can really apply this compositionality into planning. And yeah, I saw someone's raising their hands. If they want to ask on the Q&A, I can answer. Okay, so let's go back to the idea of planning. So in general, my research has been driven towards this goal of trying to get robots that can solve a wide variety of tasks. So as people, we can solve a huge number of tasks. So we can, if we want to make a BLT sandwich, we can go outside, we can get some tomatoes, we can cut the tomatoes, we can cut lettuce, and so forth. So as people, we can do a huge number of different tasks. And what we really want is we want to construct robotic agents that can likewise solve all types of different tasks. And I think the biggest issue is the issue I talked about earlier in the talk, where it's really hard to get demonstrations of cutting lettuce in every single room you can find your robot in. And then it's difficult to then gather demonstrations of finding tomatoes in every single possible room. So the space that we want to capture demonstrations over would be infinitely large if we had to cover the entire distribution that we would want our system to operate over. So we can take this idea of a compositionality and use this to really more effectively model the distribution that we care about. And what this means is now, instead of learning a single generative model over demonstrations, we can simply learn a generative model over possible dynamics in the environment. And then we can learn a separate generative model over the goals of the agent. And now by learning these two independent models, it turns out that by taking the product of these two independent models, we can construct a hybrid model that can generalize far outside the demonstrations we've seen before. And the idea is now we're encoding these demonstrations into two separate parts, one part about dynamics and one part about goals. So now if I can take the goal I see in environment 1 and apply it to environment 2. So this factorization allows us to stitch together information from one task and apply it to another task. And this type of decomposition actually corresponds to planning. And this has actually been studied a lot in model-based planning. So really a simple form of this composition is you essentially learn a state action transition model and use this to form a trajectory of states and actions. And now you learn a separate reward function that predicts rewards at each state. And now when you have a particular reward or task that you want to optimize, you can essentially just simply optimize for a sequence of actions that maximize your final reward. But actually, it turns out that this procedure, which is very simple, actually does not work that well because you often enter these adversarial states where the reward function estimate becomes very high, but it's not because the state actually gets high reward. You're just finding an adversarial example to your reward function. So it turns out that energy-based models and the machinery I talked about earlier provides you a system that can allow you to avoid these issues. And the idea is you learn an energy-based model over entire trajectory. So now we have a trajectory of states and actions, and this whole trajectory gets assigned a single energy. And now if any pairwise transition in the trajectory, so let's say between state 1 and state 2, has inconsistent dynamics, the energy is predicted to be high. And only if every single state and action has consistent dynamics is the energy predicted to be low. And this parameterization of trajectories using energy-based models actually allows you to avoid adversarial minima because the energy function has been explicitly shaped to have low energy only at trajectories with dynamics that you have seen before. So because you're explicitly shaping the energy landscape, now when you optimize it, you won't get these adversarial examples. But it turns out you do lose something. So if you learn an energy function at the trajectory level, and you've only seen trajectories in blue and gray, it's really hard to make trajectories that can go from this black dot to this star. To actually generate these trajectories by simply making the energy function itself compositional. So you can just learn energy functions over pairwise transitions and use that to construct this trajectory, or you can induce the architecture or this energy function to be compositional at the architectural level through temporal convolution. So once we have this trajectory level energy function, we can now use the same procedure we talked about earlier. So we have this trajectory level energy function. We can simply just use a separate energy function to encode your goal, a value function, or test time constraints. And now by just composing these two energy functions together, you can now implement planning or reinforcement learning at test time. So the first thing you can do is you can implement reinforcement learning. So you can take an energy function, which is just a reward function that you learn for a particular task. And now by just composing these two models in a zero-shot manner, you can do offline reinforcement learning. And what we find that this modular approach, where we don't actually do any reinforcement learning during training time. So training time, we just train this trajectory level energy function, allows you to perform as well as state-of-the-art offline reinforcement learning techniques. But the benefit of this compositionality is that it allows you to do a wide variety of other tasks. So another task you can do is you can take this trajectory level energy function. You can just simply define a separate energy function that just specifies that I have to be at a start state S0 and I have to be at a goal state G. So if my trajectory doesn't satisfy this constraint, the energy is infinite, and only if it satisfies this constraint is the energy low. So if we take the composition of these two energy functions, we now get a new composite energy function that allows us to plan. Because it will only generate trajectories that have consistent dynamics that satisfies our start state and our goal state. And we find that this approach allows us to take these environments where we train this energy function on random trajectories in the maze. And by just fixing a start and goal state, generate these long horizon plans where the length of the horizon on the right is 512. So this allows us to do zero-shot planning. And in general, this zero-shot planning is really flexible. It requires no training. So we can both do it on single task planning, where we have one start and goal state, or multitask planning, where we have many start and goal states. And what we find is that baselines, which are offline reinforcement learning approaches, require per task training. So you would have to train separate models for these two tasks if you were not using this compositionality. And finally, this type of compositionality also allows you to combine cost functions. So you can take an energy function for trajectories, and you can simply define a separate energy function that defines a set of costs on states. And now you can do trajectory optimization. So let's say you have an energy function for stacking blocks. You can simply just define three cost functions. So you can say that I want the gray block on top of the purple one, the purple on top of the red, and the red on top of the blue. And now you get energy, and now you get a behavior where you stack the blocks in a particular order. So you can combine these energy functions with cost functions that can either be learned or hand constructed. And finally, this type of planning procedure can be done even if you don't know the ground truth state. So if you have an image observation, you can just define your energy function over future states and actions given this image observation. And a particular instantiation of this approach corresponds to diffusion policy. So in this setting, we trained our approach on 50 demonstrations of executing this task of moving this mug upright. And now the system, through this energy minimization planning procedure, is able to do all types of dexterous manipulation tasks. So, where you can see that it can try several times until it's able to upright the mug, put the mug in the right direction. It can and this type of planning system can also be used to spread sauce. So here we're spreading sauce, and even when people perturb it, the system is able to reliably spread sauce. And you can also generalize this planning procedure to many different environments by using the image space. So previously, I talked about how you can combine this energy function across states and actions. But one issue is if we want to learn one energy function across many environments, then the state and action spaces are different. So we can simply just use images as a unified abstraction across many environments. So now our energy function just predicts a video of the actions we want to take. So this allows us to have a single model that can synthesize this plan, where we want to pick up the orange cube and place it next to the red cube, but also have that same energy function also generate a plan of taking a sponge and wiping a board, as well as picking up silverware from the dishwasher, and so forth. So essentially, this procedure also allows us to use images as abstraction for planning. And the benefit of this is now once you have these images, you can just use the simple, because these images are very high fidelity, you can use the inverse dynamics model to infer the actions you want to take in the environment. And this also allows the video space planner to directly learn from videos on the internet. So there are a lot of videos of people opening doors, and you can essentially use these videos of people opening doors as additional data to train your planner when you do these plans in the image space. And yeah, I saw the so can you use the E2 energy function during training and not just during test time? Yeah, you definitely can use it for both training and test time. So it probably, if you train it with E2, then probably the composition will work better. And one thing to note is that these video plans are highly realistic and detailed. So that was put banana in a pot or pan. Or if you consider the task to flip a pot upright in a sink, you can see how it looks very physically real. So given these highly detailed videos, then it's easy to imagine how you can extract actions to solve each of these tasks. Cool. So in the last section, I talked about a particular type of compositionality of a dynamics model and a goal model. So finally, I'll talk about how you can really use this planning more broadly across multimodal models. So let's consider a really complex task of making a cup of tea. So this task is really complicated because it requires many different sources of knowledge. On one hand, you need to have some common sense knowledge. So you need to know where to look for a tea kettle. And you need to have some visual knowledge. So you need to know what the 3D geometry of the world, as well as the identity of objects. So you need to know what a teacup is. It requires some physical knowledge. So you need to know how heavy things are and whether you can pick up something or not. And you need some control knowledge because you need to know how to actually grasp an object or open a cabinet. So you need all types of knowledge. So you can imagine that if we want to train an embodied agent to solve these super long horizon tasks, it would be almost impossible to get demonstrations to cover the entire space of data we want the system to operate over, because we need to have all combinations of different scenes, of different types of grippers, of different types of physics, of different types of visual appearances. So the space of demonstrations gets exponentially larger. It turns out that you can use this idea of compositionality to actually solve this long horizon task in a zero-shot way by simply combining existing foundation models. And roughly, what you do is you use a language model to capture semantic information, and you can use a video model to capture visual information. But you can essentially decompose this large high-dimensional space that you want to learn a long horizon decision-making system over into a set of factors or axes that are parameterized by existing foundation models. And then this allows zero-shot generalization, even if you have no data. So just briefly, to compose different foundation models together, we need a little bit more machinery. So it turns out that you can interpret any type of pre-trained model or foundation model as an energy function. And the idea is you can just take the loss function the model is trained on as your energy function. So if you have a large language model, you can take the input language, or you can take the negative log likelihood the model is trained on as its energy function. So that if a language instruction is in distribution, the likelihood loss is low and the energy function is low, and otherwise vice versa. In a similar sense, you can convert a clip model into an energy function by using the language vision alignment losses trained on. So if a language embedding and image embedding have low energy under that loss function, then it's in distribution, and otherwise it's out of distribution. So the loss function gives you a natural energy function for any pre-trained foundation model. So let's see a brief example of how this is powerful. So let's consider a visual question answering task, where we have the question, what is a cat doing? And you have this corresponding image of a cat in the garden. Now, by default, a large language model cannot solve this task because it can't see the image. So it can generate plausible answers, but it doesn't actually generate answers that are grounded in vision. And in the same way, a clip model cannot solve this task because it actually cannot parse the question. So it can generate different language that matches this image, but not language that answers this question. But it turns out that you can use this energy function machinery that I talked about earlier as a way to really solve this problem. So solving this VQA task actually corresponds to simply getting a response that minimizes the first energy function. So we want to get a response so that the response aligns well with the image, so it has low energy under the clip model. And we want to get a response that has low energy under the second model, so that it is a plausible response given this question. So if we can just simply optimize these two energy functions defined by the losses each model is trained on, we can solve this VQA task. And a small caveat is, in practice, you can't actually just use the same machinery we talked about earlier of gradient descent to optimize these two energy functions because the responses are discrete. So there is no gradient. But you can use a similar idea where you can use one model to help your optimization of these two energy functions. And essentially, the idea is you can approximate optimizing these two energy functions is simply drawing samples from the language model energy function and finding ones that minimize the first energy function. So roughly, it looks something like this. So initially, you take the language model, it generates a response to the question, what is the cat doing? And the response is, the cat is catching a mouse. And now you try to optimize. So given this response, you take the clip model and you get an energy value for this response. And you can use this energy value to help you optimize. So you can try to find a response that minimizes this clip energy function. So you might get an intermediate answer now of the cat is walking to a yard. And after a bit more optimization, you'll finally get the correct answer of a cat is walking in a yard. So by simply just optimizing these two models, you can solve this VQA task. So overall, this type of energy optimization is kind of a zero-shot way to combine information across models. But now let's look a bit more at this task that I talked about earlier, where we want to construct a plan to make a cup of tea that is semantically, geometrically, and physically executable on a robot. So if we consider the task of making a cup of tea, a language model is certainly very useful for this task because it can tell you to look for a tea kettle, to heat the water, and to find a tea bag. But it doesn't actually allow you to solve this final task of making a cup of tea because it doesn't tell you exactly how to look for a tea kettle or how to heat water. And at the same time, this language plan isn't actually grounded in the environment. In contrast, if you have a large video model, such as the video space planner I talked about earlier, this can tell you a lot of useful physical knowledge. So it can tell you how exactly you want to pour a cup of tea. But it doesn't really tell you the high-level information in the language model. And finally, if you have an action model, this action model, given an image goal, can tell you how to pick up a bowl. But again, it doesn't tell you any of the components I talked about earlier. But you can actually use this idea of compositional generative modeling or combining these energy functions to really combine these three models together. So if we can simply draw samples from the product of these three distributions, then we can actually draw samples that actually are consistent at the language model, video model, and action model. So what that means is we want to get a language plan, an image plan, and an action plan so that the language plan is plausible under the language model, which means that it is semantically plausible. And at the same time, we want to make sure that that language plan also has an associated image plan. So that means that the text plan is grounded in the environment so that the video model can generate a plausible video. And we also want to make sure that the video plan is plausible, has a plausible action plan. So that means that the video model can be physically executable. So by taking the product of these three distributions and being able to optimize for these three variables, we can get a plan that is consistent across all three of these levels. And the actual optimization ends up looking very similar to the procedure I talked about earlier. So if we have a goal of stack a red block on a cyan block and place a brown block to the right of the stack, initially the language model might say something like place a cyan block in a brown box because it doesn't see the visual input. And then you have a generated video that's impossible. So you can use this video model's energy function as feedback to generate a new plan. And the new plan will be place a white block in a cyan bowl, which in this environment allows you to solve this task. So essentially, you can use this iterative refinement procedure to allow you to compose all three of these models together. And finally, this composition allows you to solve these tasks, these long horizon tasks, where here we can stack a red block on top of a brown block and place a yellow block to the left of the stack. And as a final thing, it turns out that this composition between the language model and video model ends up being a bit slow because the language model will often generate these plans that are not necessarily grounded in vision. And even if they were grounded in vision, the video likelihood ends up being a likelihood that is really hard to optimize. So we can actually use a bit of a cross-modal structure to make this a bit faster. So instead of using just the language model to capture your task information, you can actually use a vision language model. So the vision language model will take an image, and then it will predict these. Now it will predict these visually grounded plans. And you can also use the vision language model as a heuristic to help accelerate your consensus procedure. So roughly what this means is now instead of using this language model that takes in the goal, put the fruits in the top drawer, now you have a vision language model that takes in the input image as well as the goal, put the fruits in the top drawer, and it predicts two possible actions. One is place the banana in the top drawer, and the second action is open the top drawer. And now once you have these possible text actions, the video model, similar to the previous setting, renders these actions. So if we have the action, place the banana in the top drawer, well, there's no top drawer that's open. So now the video model simply just drops banana. In contrast, if we take the plan, open the top drawer, now the video model generates a video of the drawer being opened. And now finally, instead of using the video likelihood to select what is a plausible video plan, we now use the vision language model to assess how good each video is. So if we take the first video, the vision language model assesses that it's a bad video. In contrast, if we take the second video where we're making concrete progress towards opening the drawer, the vision language model now assesses that this is good progress toward the final goal. And now we can combine these two models together to do tree search. So now the vision language model predicts two possible actions, either opening the top drawer or placing a banana in the top drawer. We select the best one. And then we select place the banana in the top drawer. And now we have three possible actions in step 3, which is shown here. We can either close the top drawer, place the apple in the top drawer, or place a Coke can in the top drawer. And we again select the one that makes the most progress. And then by repeating this process multiple times, we can implement the search to find this final long horizon plan. And essentially, and the last thing, it turns out that we can use existing language. So we can take existing foundation models and compose them in this way. So we can train a vision language model on some manipulation tasks. We can train a separate video model, train on just internet video with some demonstrations of manipulation. And we can also take an action model trained on some set of demonstrations. But what we can do is we can combine these models as in a zero-shot manner to solve a new task. So we can take a goal of put fruits in the top drawer. And even though the vision language model, the video model, and the goal condition model are not explicitly trained at all on this task, their composition can successfully solve the task of putting fruits in the top drawer. And here it fails, so we replan. But eventually, the system is able to solve the task of putting fruits in the top drawer. So this approach enables zero-shot generalization. And as another example, we can take this input image shown here. And then the system can synthesize the sequence of language plans. And actually, the sequence of language plans actually corresponds to the synthesized video for how to make a line. And so this is a fully synthesized video. So you can see that this procedure can synthesize a very detailed plan that allows you to make a line out of the blocks. And you get these corresponding language instructions. And then you can also execute this in the real world. And we also compared this quantitatively against a variety of robot foundation models. And what we find is that this hierarchical approach, that is zero-shot, allows us to much more accurately solve long horizon tasks. So if we train a large video model, which is this red bar, it performs poorly because the video planning task is too complicated. If we train an end-to-end policy, it also fails because the task is so long horizon. But by using this composition of models over different hierarchies, we're able to successfully accurately solve this task. Great. So overall, what I've talked about a bit about is generative models and how generative models really can be built compositionally and how they can enable us to generalize both in planning as well as in multimodal models. Thanks everyone for listening, and happy to take any questions now.
Yeah. Thank you so much, Yilun. It's a great talk. And I think there are two more questions in the Q&A. And before that, I remember someone raised hand. Yeah, I'm seeing. Let me see if he's still here. Srinivas. Sorry, Srinivas, I allow you to talk. If you raise your hand, if you like to talk, you can unmute yourself and ask a question. Srinivas?
Hello, Dr. Dianmo. Yeah, okay. The primary question is in one of your work, the loss function finally it looks similar to Weierstein GAN.
Mm-hmm.
So, and what's the major difference between your loss function and the Weierstein GAN? That is my primary question.
Yeah. So yeah, one of the actual maximum likelihood training objective for energy functions looks the same as Wasserstein GAN. The big difference is here in Wasserstein GAN you have two networks, a discriminator network as well as a generator network. So here we assess here the discriminator is your energy function, and now your generator is simply the MC on the energy base. So essentially, it kind of combines. You can interpret under this interpretation that objective corresponds to maximizing the likelihood of the energy base.
Okay, sure. Thank you.
There are three more questions I think in the Q&A. panel. Maybe we can.
Oh, great. Yeah, so I guess the first question is if there are any possible principles or inspirations on designing the energy function, such as the plan for safety or speed. Yeah, so I think I think yeah, one big thing about these energy functions I've talked about so far is a lot of the ways I compose them are I explicitly construct a particular structure to compose the energy functions. And the way I compose them is based off existing domain knowledge. So for instance, in planning, I know that I should compose a dynamics model with a goal model. So in general, trying to construct methods that can actually automatically discover the compositional structure is really interesting direction for future work. And also, in general, this system can be in general when you're optimizing these energy functions, it could be hard. It can be slow to optimize each of the energy functions, but depending on the way you optimize them at test time, you could make it much faster. So, for instance, you could first optimize for a hierarchical for a very coarse plan at a high level, and then refine it with subsequent energy functions. So I think there is a lot of potential future work that you could do in actually like figuring out how you can optimize very complex compositions of energy functions. Okay, so that's the first question. And then the second question is, so it seems like this compositionality is pretty promising towards robotic generalization. What is the main open research challenges that are standing in the way of the approach for solving the issue entirely? I think one pretty practical issue with a lot of this planning procedure is actually, it turns out it's very slow. So because if we look at the tree search procedure I talked about earlier, I now have to generate a number of video plans. And then I need to roll the video plans forward to generate more video plans. And so the search procedure overall is a very slow process. So if you really want to use this approach in practice, there's a lot of performance optimization techniques you need to apply this approach. So I think I think a lot of these compositions do allow you to solve a variety of tasks you haven't trained before explicitly. But the big issue is to use them in practice, you really need to make it much faster in speed.
I got a follow-up question on that. If this tree-based research on video planning is slow, I guess at least partially it's because of the videos they are generating. Can we just do the entire planning in the latent space instead of in the video space?
Yeah, I think that could be a good idea. Yeah, I think you definitely could just do it in the latent space. I mean, the video space has some advantages because it's very visualizable. You know what's going on. It's hard to get a latent space that works for any image observation, right? Because a lot of times when you have latent spaces, they work well for your particular data set, but maybe not so well for other data sets. But yeah, in general, I think latent space could be a very easy way to just speed up the process.
Great. I mean, any more question? I already answered the last question, which is the recording of the talk. We will process a little bit. We will seek approval from Dr. Du, and once that will be ready, it will be posted both on YouTube and our website. So that's answer your question, I think. Yeah. Yep. Any more question? Okay. Oh, there's something.
I have one question, one final question. It's this is in general related to the world model concept. Uh, like according to you, what should be the ideal world model? Like, is there any concrete definition of world model from your perspective?
Sure, yeah. Yeah, I guess I've been using this world model concept very vaguely. To me, I think a world model should be a model that can simulate, on one hand, that can simulate the future. So you can, I guess towards later on in the talk, I talked a lot more about like dynamics models. But in general, I think a world model is roughly something that can, if I propose an action, it can enable me to simulate what would be the results of the action. And in a sense, these energy functions provide one way of doing that. I think the ideal world model should be built compositionally. So I think we should have the model like each part of the model capture different parts of a scene. So like maybe a world model of the physical world should have one part that models agents, one part that models physics between two objects, one part that models the goals of a particular agent, maybe the rules of like locomotion, So like each of these parts should be encoded separately, but roughly a world model should be something that simulates the results of actions.
Yeah. Thanks for your answer. Thank you.
Thank you.
Any more questions? Okay, if not, thank you so much, Yilun, for the nice talk, and looking forward to see you in Vienna.
Yeah, great. Yeah, thanks so
so
much for
much.
hosting.
Yeah.
Okay, thank you. Okay, bye.
Bye bye.